This video is for Physics of the Universe, Unit 1.3, using vectors and scalars to describe motion. Today's essential question is, what are the differences between vector and scalar quantities? Hello, baby birds. Let's begin with something we've all experienced or at least seen, running a race. Picture yourself on a track, lined up with others at the starting line. You hear the signal, and you start sprinting. Then you finish the race, and someone tells you that your time was 12 seconds. That is helpful information. It tells us how long you ran. But what if I asked, what direction did you run? North, south, around a curve? The moment I ask about direction, we are entering a different kind of thinking. We're not just talking about how much, but about where and which way. That is the fundamental idea behind today's video. In physics, we describe motion using two types of quantities. First, scalar quantities tell us only the magnitude, meaning how much. For example, time, distance, temperature, and mass are all scalar quantities. And secondly, vector quantities. Vector quantities give us both magnitude and direction. These are things like displacement, velocity, acceleration, and force. So in our race example, time is a scalar quantity, but your displacement, how far and in what direction you moved, is a vector quantity. Understanding the difference between these two is critical in physics because it determines how we analyze and solve problems. Scalar quantities are the simpler of the two types. These are measurements that tell us how much, but not which way. They don't have a direction attached. In our race example, you might hear someone say, I ran 5 kilometers, or it took me 30 minutes. Both of these are scalar quantities. They give us a number and a unit, like 5 kilometers or 30 minutes, but they don't say where the person ran. Other scalar quantities include mass, meaning how much matter is in an object, time, how long something takes, energy, how much capacity something has to do work, or temperature, how hot or cold something is. Scalars are added using normal arithmetic. If you run for 5 minutes and then add another 10 minutes, your total time is just 15 minutes. It's simple math. But remember, if you only use scalar quantities, you can't fully describe motion in space. You'll know how far or how fast, but not where or in what direction. For that, you need vectors. Now, let's add that layer of direction. This is where vectors come in. If I tell you that I ran 10 meters north, I've given you both the distance, the 10 meters, and the direction, north. That's a displacement, which is a vector quantity. Some common vectors in physics include velocity, which is speed with direction. For example, 5 meters per second east. Displacement is a vector quantity. It's the change in position with direction. For example, 100 meters west. Force is a vector quantity. It's a push or a pull with a specific direction. For example, 15 newtons downward. Acceleration is a vector quantity. It's the change in velocity per unit time in a specific direction. We represent vectors using arrows, and the length of the arrow shows how large the vector is, that is to say, the magnitude. The direction of the arrow shows the direction of the vector in space. In diagrams, you might see vectors drawn with arrows pointing up, down, left, right, or even diagonally. For example, you could see a velocity of 67 meters per second east, force equaling 13 newtons downward, and acceleration at 45 meters per second squared to the right. These all tell a full story, not just how much, but where. So let's take a moment to compare scalars and vectors side by side so the distinction is crystal clear. Scalars are quantities that have only magnitude. That is, they tell you how much of something you have. For example, if you say the race took me 10 minutes, you've been given a scalar. There's no indication of direction, just an amount of time. On the other hand, vectors have both magnitude and direction. Saying I ran 5 meters north tells us not just how far you moved, but also where you moved. That makes it a vector. Consider the following analogy. Scalars are like telling someone how much money is in your bank account. I have $100. Vectors are like telling someone you spent $100 sent $100 to a specific person at a specific location. Directions matter. You also need to be careful when combining quantities. You can add scalar quantities with regular arithmetic. But vector quantities require direction-aware methods like head-to-tail diagrams or components. And most importantly, you cannot mix different types of vectors or mix scalars with vectors. For example, you can't add a velocity vector and a force vector just because they both use numbers and units. They represent completely different physical concepts. In summary, this distinction between scalar and vector may seem small at first, but it is essential. Confusing them can lead to incorrect problem solving and misunderstandings about how objects move in the real world. So let's go back to our running example. Say you jog 3 kilometers east, then turn and run 4 kilometers north. How far are you from where you started? The answer is not 7 kilometers. That only tells you the total distance, which is a scalar. To find displacement, we need to account for direction. These two runs form a right triangle. We can find the straight line distance using the Pythagorean theorem. So displacement is going to be 3 squared plus 4 squared, which is equal to 9 plus 16, which is equal to 25. But to solve for displacement, we square root that, bring the 25 down to 5 kilometers. This is one way of doing vector addition. There are several methods. There's the head-to-tail method, where you line up vectors end to end. There's the component method, where you break vectors into parts that go along the x and y axes and then add those separately. And then there's the parallelogram method, where we use geometry to build a parallelogram and find the diagonal. These methods all consider direction. That is the key difference between adding vectors and scalars. Vector math is directional math. Understanding vectors isn't just about schoolwork. It's essential in real-world jobs. Think about a pilot. If they went to fly due north at 200 kilometers per hour, but the wind is blowing from the west at 50 kilometers per hour, their actual path is northeast. They need to do vector addition to figure out the right heading to reach their destination. Or imagine a kayaker paddling across a river. If the river is flowing downstream and they're trying to paddle straight across, their path will curve. Again, they need vectors to chart the correct angle. Even in construction and engineering, when designing buildings or bridges, forces act at angles. Engineers must calculate how these forces combine, often in multiple directions. That means breaking vectors into components and analyzing them with precision. So let's clear up some confusion that often trips students up. Speed versus velocity is a big one. People use these terms like they're interchangeable, but in physics, they are not. Speed is a scalar. Velocity is a vector. If I say 60 miles per hour, that's speed. If I say 60 miles per hour west, that's velocity. Another mistake, assuming vectors can be added just like scalars. Nope. If I walk 3 kilometers north and then 3 kilometers south, my net displacement is 0. But my total distance traveled is 6 kilometers. Direction changes the outcome. And finally, Be careful not to mix types of quantities. You can't add 5 newtons of force to 10 meters per second of velocity. That's like trying to add apples and seconds. They're different concepts, even if they both have numbers. So to wrap up, scalars are simple quantities, just magnitude. You can add them like regular numbers. Vectors include direction. They require careful, directional math to combine. And vectors are everywhere, in races, flights, river crossings, and engineering. So next time you want to think about running a race, don't just ask how far, also ask which way. At this point, you should be able to generate a full and appropriate response to today's essential question. What are the differences between vector and scalar quantities?